In this screencast, we're going to use the NTU effectiveness method for a parallel flow heat exchanger to find the overall heat transfer coefficient, or U. In this concentric heat exchanger, we have water that comes in at 40 degrees C and is heated up to 140 degrees C by hot gases that come in at 350 degrees C. How are we going to solve for the overall heat transfer coefficient? By definition, the number of transfer units, or NTU, is equal to U times A divided by C sub min. And our C, which is known as the heat transfer rate, can either be the mass flow rate of the hot fluid times its heat capacity, or the mass flow rate of the cold fluid times its heat capacity. And you calculate those heat capacity rates, and C min is the one that is the smaller of the two. Our U is going to equal NTU times the C min divided by the area. Next, we have to find our NTU. This NTU can be found as a function of effectiveness and tables for appropriate flow relations. And for parallel flow, this is going to equal minus the natural log of 1 minus this effectiveness multiplied by 1 plus C sub r, and this is divided by 1 plus C sub r. This is the ratio of the minimum heat capacity rate divided by the maximum heat capacity rate. Next, we have to find our effectiveness. And the effectiveness is the heat transfer rate divided by the maximum heat transfer rate. And this is equal to the heat capacity rate of the hot fluid times the difference in temperature of the fluid coming in and out, divided by our minimum heat capacity rate times the temperature of the hot fluid coming in minus the temperature of the cold fluid coming in. Now that we have that effectiveness, we can calculate our NTU. So what's our plan? First thing that we're going to do is calculate all of our heat capacity rates. So that means our hot heat capacity rate, our cold heat capacity rate. From that, we can figure out what our minimum heat capacity rate is, and then find the ratio of C min over C max. Once we know that, we can solve for our effectiveness. This allows us to use the relationship between the two to solve for NTU. And finally, once we have NTU, we can solve for our overall heat transfer coefficient. Let's get started. C sub C, or our cold fluid, which is the water, this is going to equal 4,197 watts per Kelvin. We do the same for the hot fluid, the gas, and this is going to equal 1,900 watts per Kelvin. So this is going to be equal to our C min, Finally, we have to find the ratio of these heat capacity rates, and that's equal to 0.45. The next thing we do is calculate our effectiveness. And when we calculate this, we find that we have an effectiveness of 0.8. Now we use that effectiveness to find our NTU. However, when we try to calculate our NTUs, what we find out is that this does not exist. So physically, using a parallel flow concentric heat exchanger, you cannot take water that comes in at 40 degrees C and have the gas cool down from 350 degrees to 100 degrees C. So instead, let's change some of the numbers and change one in particular. Let's say that the gas, instead of exiting at 100 degrees C, we're going to have it exit at 150 degrees C. The first thing is that that's going to change our effectiveness. And we're left with an effectiveness of 0.645. Now when we put this back into our equation for our NTU, we end up with an NTU of 1.9. And we end up with an overall heat transfer coefficient of 181 watts per meter squared K.